to reach the center of the pellet, that reduced, which basically meant that in a smaller pellet, most of the reaction would take place through the entire pellet, almost as if, so the top of the pellet as well as the middle of the pellet would pretty much see same amount of concentration. If not, the reaction rate would have been different. Okay, what I mean by that is, if you have a 1 mm pellet, okay, and in today's lecture I will come to what that 1 mm is going to be. Okay, if you have a 1 mm pellet, okay, the concentration that the catalyst sees over here, the concentration that the catalyst sees over here, the concentration that catalyst sees over here is approximately the same. Okay, when it comes to a larger pellet like this, concentration at this point, concentration of this point, concentration of this point are different. This concentration is equal to CAS, this concentration will be less than CAS, is going to be further less than. Okay, so as we go along the pellet, the concentration keeps decreasing. Okay, as a result, when the concentration was same, okay, the net rate of reaction through the entire pellet remained unchanged, in the sense that your eta was approximately equal to 1. Okay, what is the eta? Eta is nothing but K absorb K ideal multiplied by CAS. Okay, so that was what we saw in yesterday's tutorial. What we did not yet see is that how the concentration changes. Okay, but the consequence of this change in concentration is something that you have already seen. Okay, so now let us go over the derivation. Okay, and why this is relevant is because the catalysts come in different sizes and shapes. In fact, when we do our reaction studies in the lab, we literally calculate the Thiele modulus, and there's an equivalent concept called Weiss-Prater criterion. So we actually calculate that and ensure that the system does not have internal and external diffusion resistances. If the system has internal and external diffusion resistances, the activation energy, for example, that you calculate is not the representative or correct activation energy, because the overall reaction is limited by diffusion as well. Okay, so those are the things that, whether it is industry or whether it is research, we first, once we start analyzing a particular catalyst, we first verify that this overall system does not have external and internal mass transfer resistances. How do we check external mass transfer resistances? Equivalent of k dash kg divided by k plus kg. Okay, that we talked about yesterday, right? So eta external should be approximately equal to 1. How do we verify this? We verify this through the Thiele modulus. Okay, so that is what we actually do in the lab as well. Okay, and at various stages of scale up. So let's say in the lab we did analysis with this. Okay, and then we went to this in pilot scale. Okay, we do analyze at pilot scale whether or not the system is going to be mass transfer limited. Okay, oftentimes we cannot help it, we cannot have really small catalyst particles, because then the pressure drops are going to be very high. We will see this example in module number 9. Okay, so therefore we cannot really have small catalyst particles if you have a very large reactor. So there needs to be some kind of trade-off. But what that trade-off is, how it happens and all that, for analysis of this, we do use Thiele modulus, and there's actually in research we use a slightly different concept called Weiss-Prater criterion, and that is there in your textbooks, both your textbooks. So you can read up about it. We won't talk about it in this course. Okay. We talked about diffusion within the pores, Knudsen diffusion, overall diffusion, and the effective diffusion, that's because of porosity and tortuosity. Okay, and you have also done a problem in the previous tutorial. Okay, this is where we were, that the overall model is like this. Okay, now what are going to be the boundary conditions? Okay, so this is the slab. Okay, and then the slab, let's say there is flow that is happening, or everything might be quiescent, doesn't matter how the situation is, and the concentration over here is CAS, concentration over here is also CAS. Okay. This is the center line. Okay, this is 0, this is L. Okay, at center line, because everything is same, from if you go in this direction versus you go in this direction, because everything is same, you are going to have the flux at this particular point to be equal to 0. Okay, these are standard boundary conditions. Okay, the boundary condition at the center is going to be dCA by dZ wave. Okay, now this is something that all of your engineering courses you would have done. This is how the center line conditions always are. Now, why are the center line conditions like this? Is because if everything is mirror image, that means your profiles might be like this, your profiles might be like this, whatever it is, the d by dz at this particular point is going to be 0. And whether it is cylinder, whether it is square, whether it is rectangle, whatever geometry it is, okay, whenever there is a axis of symmetry or a point of symmetry or a location of symmetry, this is the symmetry boundary condition. Okay, so this is the boundary condition at L or Z equal to 0. This is the boundary condition at the edge. Okay, we are going to apply this to slab, cylinders or sphere. Okay, when it comes to the slab, okay, this is what you are going to get. Okay, you can very well solve it in this form. You do not need to non-dimensionalize it. Okay, the advantage of non-dimensionalization is that you can use the concepts irrespective of the size of the particle, and with generalized Thiele modulus irrespective of the shape of the particle also. Okay, so that's the advantage of non-dimensionalizing. So if the question, so I remember when I was younger, the question I would ask the question, why are we doing this non-dimensionalization? My answer would be, because it is always done like that. No, there is a reason why it is always done like that. The reason why we work with non-dimensional quantities is because you can analyze a particular system independent of the size of the system. Does not mean that the size of the system does not matter. It does, and the example is right there in front of you. A thin slab versus a large slab, the size mattered when it came to whether or not it is diffusion limited or not. Okay, the analysis is independent of the size. The results are not independent of the size. Okay, your algorithm is independent of the size. Okay, if you were to not do non-dimensionalization, okay, your analysis for a particular geometry will still be independent of the size. But you will have to do one analysis differently for a slab, you will do another analysis differently for a sphere, you will do a third analysis differently for a cylinder. If it is a wash coated catalyst, you will do one more analysis independently. Okay. Whereas if you work with non-dimensional quantities, the algorithm remains the same. Okay, the expressions may or may not be the same, but the algorithm remains the same. Now, example of expression remaining the same is the generalized Thiele modulus. We'll come to that at the end of this lecture. Example where the equations change was what we did with external diffusion. Okay, single particle, we had one Sherwood number correlation. Foams, we had another Sherwood number correlation. Packed bed of sphere, we had a third Sherwood number correlation. But the procedure was the same. What did you do? You calculated Reynolds number, you calculated Schmidt number. From that, you used different expressions based on the situation, based on the geometry. You use a different equation, but got what? In all cases, you got Sherwood number. Once you got the Sherwood number, you calculated your kg. Okay, this part remained the same, this part remained the same, this part changed based on the geometry. This part also remained the same. So you could follow a particular way of doing things, a particular uniform way of doing things. Okay, that's the reason why engineers, whether it is chemical engineers, mechanical engineers, aerospace engineers, we just love our dimensionless numbers. Okay, and this is not restricted to CRE only. This is universal, not restricted to the chemical engineering either. Okay. Oops. Yeah, this is where we are. Okay. So, how do you convert this into non-dimensional? Ca equal to Ca naught multiplied by zeta, Z equal to L multiplied by another quantity. Okay. And when you do that, and we did that in the previous lecture, we can rearrange to get this in to get the Thiele modulus. Again, just for sake of completeness, how do you do this? Is 0 equal to d okay. If you take this on the Ca naught, gets cancelled, and therefore you will have 0 equal to okay, and this equation has a particular form. Remember first semester math, right? D minus m multiplied by d plus m, y equal to 0. D minus m will give you e to the power my my. D plus m will give you e to the power minus my. Yeah, you can use any of the first semester math calculus math books, or this would be done by Professor Pushpavanam in his math course right now. Okay. These are standard mathematical equations, standard ways of solving. Okay. I will erase this because it is there in the next slide, I think. Yeah. Yeah. So, this is what we have. This can be written in this form, and this will then have a form like this. Okay. Now, the next step is to find your A and B values based on your boundary conditions. Okay. Whenever your boundary condition is something equal to 0, that is an easier boundary condition to apply. Okay. What is the easier boundary condition to apply in this case? It is y dash equal to 0 at z equal to 0. That is an easier, or Ca dash equal to 0 at z equal to 0. That is an easier boundary condition to apply. Okay. So, if you apply this, you will be able to get one expression. Okay. And this expression basically says that either m equal to 0, okay, which is a trivial solution, okay, or A and B are related. Okay. Then you apply the second boundary condition, and once you apply the second boundary condition, and the derivation, the detailed derivation is there in your textbook. You apply the second boundary condition, you will basically get your concentration in this particular form, okay, or okay, and this we will just write by Z by L. Okay, where phi what D? D effective. Okay, where do these guys come from? These guys do not come from module 5, they come right back from module 1. Okay, Kca or K dash or KVCa is the net rate of reaction in moles per second, which is equal to Ka Ca, K dash multiplied by A multiplied by Ca, which is equal to K dash multiplied by mass multiplied by Ca. Okay, we have gone over that a few times. Okay, so this is the expression that you are going to get. Okay, and that is summarized here. Okay, so this is just written over here. Ca within the particle has a expression of this form, exactly what I have written here. Okay. What is cosh? What is the hyperbolic cosh? Let us look at the denominator. Cosh phi is nothing but e to the power phi plus e to the power minus phi. Okay. You are more comfortable with e to the power, you can very well use e to the power. It is exactly the same, it is just written in slightly different way. Okay. This is just a shorter representation. If you were to write e to the power, it becomes just much longer. That's the reason why it was written in this form. Okay. Remember when all of this was derived, yeah, people used to use pen and paper. Okay. Any questions? Let's look at the example that we took last time, right? So this was the example. Let's open Excel. What we are going to do is, let's say we have the pellet. At the boundary, the concentration is, well, not given. At the boundary, concentration is 1. Okay. We want to see how the concentration changes within the pellet, okay, using the equation. Okay, so let's do that. Okay, what do we have? Diffusivity, the effective we calculated as 10 to the power minus 5, right? Yesterday's calculations. Our K was 1.5. One mm pellet. Phi, our Thiele modulus is, you can see this, you cannot see this. You cannot see what is happening, is it? Now? Yeah? Okay. Okay, phi is what? It's equal to L multiplied by square root of K by D. Okay. Our eta yeah, these are the things that you calculated yesterday. Okay. What we want to do is to find out how our concentration Ca varies from edge of the catalyst pellet to the center of the catalyst pellet. Okay. So, I will have our zeta yeah. Okay. I will highlight this. I will take this and just drag it until this becomes equal to 1. Okay. Our z is, our zeta was z by L. So, z is zeta multiplied by L, right. So, zeta multiplied by L, okay. And as we had done last time, we will put dollar signs here. We will just put on the row index because we are going to drag down the row. You take your cursor to the right bottom edge and double click, it will autofill. Okay. The length is in millimeters. If you wanted, sorry, length therefore, and what we are showing over here is in meters. So, if you wanted in millimeters, we could do this multiplied by 1000, and this would be in millimeters. Okay. Anyway, we will just keep it in meters. Okay. Ca as a function of z. Okay. What is Ca given by? CA is given by cosh phi multiplied by zeta divided by cosh phi, okay, equal to cosh phi multiplied by zeta divided by cosh phi. Okay. And let's double click and drag it. Oops, why did this happen? My mistake. I forgot the dollars, right? Where should be the dollars? It should be in the fee, okay? So it should be $4, $4. Okay, this is what going to happen. Okay, so let's now plot this. Okay, we'll go to insert and we will plot. Okay, we'll do a scatter plot, line plot. Okay, and because you are all PG students, I'll spend maybe next 3-4 minutes to show how for your MTech project reports, for your MS reports, for your PhD reports, you should make the plots. 90% of you, when in your first report or your first documents, you will just copy paste plot like this and put it. Okay, my students should never do this. This is what I expect of all my students. Okay, you should use the plot in an appropriate manner. Okay, and I'll show you what all we need to do. Delete this, this is not needed. Okay, if we are not doing anything quantitative, this is qualitative. These plots are qualitative in nature, therefore we are not going to use any grid lines. These are called grid lines. I'm deleting the grid lines. Okay, next thing, you choose this. Okay, and in the plot area, give a black color border. Okay, line should be any of the primary colors: black, blue, red, dark green, 50% green, magenta. Okay, do not use the default colors. Okay, we'll use black line over here. Okay, color of the text should be black. Oopsies. Okay, we'll use black color text. Aptos actually is a pretty decent font, so if you want to use Aptos font, yes. Okay, for papers and presentations, for papers at least, reports and papers, prefer either Arial or Times New Roman, your choice. Okay, but try to not use any other font. Okay, do not use Comic Sans, do not use, you know, any arbitrary font. It might look good to you. Okay, it does not aid readability. Actually, Comic Sans does aid readability. Okay, and look at Wikipedia and look at the history of Comic Sans, and you will see that the person who made Comic Sans thoroughly regrets making that font. Okay, Comic Sans, the name of Comic Sans is comic. When you are using Comic Sans, it means that you are criticizing something. Okay, that is the intent of the font. Okay, it's become very popular because it's a very good quality font. Okay, but my students, please don't use. Okay, can go to Arial. Okay, and font size will make say 14. Okay. Now, next thing that we want, chart design, add chart elements. We want to add titles to both x and y axis. Primary horizontal, primary vertical. What is this? This is concentration C A as a function of z. Okay, go over here, right click, font, subscript. Okay, okay, click over here. Here we want to go from 0 to 1. Okay, we want to see tick marks, major type inside. Okay, the color of the axis black. Same over here, color of axis black, and top we want it to go up to 1. Okay, we want major tick marks inside. Okay, other thing that you want to do is the size of this, you try to keep the ratio as 3:4. 3:4. Okay, so let's make the width as 12 centimeters, the height would be 9 centimeters. Okay, this is how your concentration varies, okay, from the outside of the pellet to the center of the pellet. Okay, you take that pellet, drop it like this. This is how the concentration is varying. Okay, what do you think? Is this concentration flat or not flat? What should be the concentration based on what we discussed? Okay, the size of the pellet 1 mm. So which pellet are we talking about? This guy, not this guy. What did we say about concentration in this? More or less the same. What do you see in Excel? Same? This is dropping, no? Why are you saying same? Difference is not much. Okay, it matters how you plot it. What matters is what's the y-axis. What should be the y-axis? The minimum concentration will be 0, maximum concentration is 1, right? If I do this, this is how this concentration is going to look like. Okay, now let's actually bring it up here. Let's make this length 5 mm. Let's make this length 25 mm. Yeah. Finally, what is the net reaction rate that is happening in the entire pellet? Okay. If you look at pellet, okay, the concentration is varying. Okay, the rate of reaction at this point is the rate of reaction at this point okay. What's the net rate of reaction in terms of moles per second? The net rate of reaction, if the concentration was constant, would have been Kca multiplied by volume, or Kca multiplied by Az, right? But if concentration is changing at each location, what will this be? It will just be integral 0 to L AdZ, area under the curve. Okay, if Ca is not changing with location, if Ca is not changing with location, Kcaa will come out. Integral 0 to L of Z is going to be equal to L, A multiplied by L is just V. So, Kca multiplied by V is your rate of reaction if Ca was constant. But if Ca is varying, that is not the case. Okay. If Ca is varying, you are going to integrate it. Let us go back and do that in Excel. Let us zoom a little bit lesser. Okay. Rate, okay, equal to, or sorry, let us call rate of progress. Equal to K multiplied by Ca. Okay. R into dz. Let us assume area to be equal to 1. Okay. R into dz is nothing but this guy multiplied by this minus this. Take this, drag it, take this, drag it. Oops, yeah, I again same mistake, I didn't put dollars. Be $2 should be. Okay, and this would be fine. just have to do, for integration we'll just have to change this. Not 28, sorry, 26. Okay. Now the net rate is, integration is just summation. Okay. So this is the net rate. Okay. The ideal rate is nothing but K multiplied by Ca naught. Okay. The ratio of the two is eta. Okay. So the eta turns out to be 1.3. Oh, why 1.3? Some problem I might have made. Okay, I'll correct this sheet and send it over. Okay, let's say if the length was 0.005. Okay, your rate of reaction has increased. Your ideal rate of reaction has remained the same. The net rate of reaction has increased. Okay, and this is, oh, okay, this is because I'm not using the correct integration. Okay, I have to do basically a trapezoidal method. What I will do is this particular sheet, I will correct it with the trapezoidal method and upload it so that you will see for yourself how eta works. Okay, and if the thickness of this was equal to 1, okay, net reaction rate is 1.5, eta is approximately equal to 1. Okay, why is this mistake? This mistake is because of numerical errors. Okay, the actual calculation should be first value multiplied by divided by 2, last value divided by 2, and all the middle values multiplied by 1. Okay, if you know your trapezoidal method of integration, right? So if you have two values, the integral between the two values is the area under the trapezoid. Okay, what we are doing is we are calculating area like this, and therefore there is error. Okay, I'll correct it and I will send it. I'll upload it. You'll see for yourself that your eta calculated like this is equal to the eta that we have hand calculated. Okay. So what do we have? We calculated or observed as nothing but integral dz. Our true or our ideal zero to L, right? This ratio is eta. How do you calculate the eta? Calculate the eta by doing this integration. What is, again, what did we do in Excel? In Excel, what we did is K multiplied by CAS integral of this. Integral, we replaced this by summation, right? That's what we did in Excel. with hand calculations, we have done this, and what we have done in the Excel sheet is compared this with our Excel calculation. Okay, all of these calculations you have done it yesterday. I have not really taught anything new today other than how CA varies with location. Okay, to summarize, what we have done is the way CA varies with location, if it is flat pellet, it's going to vary like this. Okay, this is what we have seen in Excel. Okay, what does this mean? Very large mass transfer limitation. Okay, only the initial part of the pellet is being used for reaction, rest of the pellet is not used for reaction. Okay, this phi equal to 0.3 means mass transfer is very fast. It's not really that mass transfer is very fast, it's that mass transfer is happening in only a small place. What are we plotting over here? We are plotting zeta is the x-axis. If instead of zeta, if I were to plot z as the x-axis, how will these three look? The way these three will look would look like this. Okay, the L equal to 25 will look like this. L equal to 5 will look like this. L equal to 1 mm will look like this. Okay, all we have done is that first 1 mm, by non-dimensionalizing we have just stretched it. So therefore you are seeing the plots like this. Okay, it's not that physically something different is happening. One pellet is very small. Okay, you are swimming 5 meters or 1 meter, 2 strokes you have reached the other end. Okay, third case you are swimming 25 meters, 2 stroke you have probably covered a very similar distance, but the catalyst has not ended yet. 2 more stroke you have kind of covered still more distance, 20 more strokes you have now covered the entire 25 mm distance. Lot more effort, lot more diffusional resistance. So therefore catalyst pellet, 25 mm catalyst pellet is not effectively used. Effectiveness factor is 0.1. It's almost as if, again don't take my statement literally, it's almost as if only 10% of the pellet is used. With 1 mm pellet, it's almost as if 95% of the pellet is used. Okay, that's the physical significance of your eta. Physical significance of your phi is how difficult it is for you as a molecule to swim through the catalyst pellet while reacting. That's the significance of phi. Reaction in the numerator, diffusion in the denominator. So if as a swimmer you are finding it difficult, your phi value is going to be larger. As a swimmer you are finding it easy, your phi value would be smaller. Okay, and it is all relative. The same effect you will get by the effect of reducing your catalyst pellet by a factor of 2, you will get the same effect if you reduce the rate of reaction by a factor of 4 or if you increase the rate of diffusion by a factor of 4. Okay, it will be the same effect. Okay, rate of reaction will not be the same. eta would be the same, phi would be the same, rate of reaction would be different. Okay, because the net rate of reaction is Kca multiplied by V, because that V is different or your K is different. Okay, so that's if this was a flat slab. If this was a spherical pellet, everything absolutely the same, your equations just change to this guy and your small phi changes to this. Okay, and what was done in this, what would be done in your second tutorial problem from yesterday, which we did not do, is if instead of the Thiele modulus, if we were to do the generalized Thiele modulus, okay, for a spherical pellet, we will compare generalized Thiele modulus with the regular Thiele modulus. Okay, that's all that is there when it comes to internal and external mass transfer limitation with reactions. This was the problem that you did yesterday. The problem that we will do next will be a similar case, but with a spherical pellet, different sizes of spherical pellet, how phi changes and how eta changes, and recalculate how capital phi and capital eta changes, and compare that you don't lose a lot of, you don't have a lot of errors by going to capital phi. Okay, that one I will put it as a part of your assignment so that you get credit for it. Okay, if you have time during the first week of October, you can have tutorial in which that problem can be solved. Okay, so that brings me to the end of this lecture. What I will upload is, well, we will upload the Excel sheet right away, but I will edit that Excel sheet to correct the integration. Okay, that's what we will do.